Have you ever stopped to think about how we know just how much natural gas is buried miles beneath our feet? I mean, it's a massive, invisible puzzle, and it's locked away deep inside solid rock. Today, we're going to dive into the really brilliant science of reservoir engineering to see exactly how the experts solve it.
So, right off the bat, here's the core problem. Imagine trying to measure the air inside a sponge. Okay, now imagine that sponge is actually a rock formation miles underground, being squeezed by the weight of entire mountains and baked at some incredible temperatures. Yeah, that's the daily puzzle for petroleum engineers.
And we're not talking about just a little pressure here. We're talking about conditions that would literally crush a submarine in an instant, and temperatures hot enough to boil water. In this kind of extreme environment, all the simple rules we learned about how gases behave, they get thrown right out the window. And understanding why they fail is absolutely key.
Okay, so here's our game plan for cracking this puzzle together. We're going to start with the perfect world model. You know, the one from basic physics. Then we'll see why it fails, and I mean dramatically fails, in the real world. After that, we'll meet the clever engineering fix that changed everything. We'll even look at how they handle gas impurities before we put it all together.
So, our story really begins with a concept a lot of us probably remember from high school science class, the ideal gas law. It's a beautifully simple model that describes how gases should behave in a perfect, tidy little world.
Yeah, you might remember this old classic, PV equals nRT. It's built on two really big, simplifying ideas. First, that gas molecules are just these tiny, volumeless dots. And second, that they never interact with each other. They just bounce around like perfect little billiard balls. And you know what? For a lot of situations right here on the surface, that's actually close enough to be useful.
But miles underground, inside a natural gas reservoir, that perfect world completely, totally breaks down. The very assumptions that made the ideal gas law so simple and elegant are precisely what make it fail so badly under these extreme conditions.
And this is where reality really collides with the theory. On the left, you've got the ideal model, pretending molecules are just these imaginary points in space. But on the right, in the real reservoir, those molecules are squeezed so incredibly tight that their actual volume absolutely cannot be ignored. The ideal model also pretends they don't interact, but down there, powerful forces of attraction and repulsion take over and completely change the game.
And this is the result. This quote from the source material really just spells it out. We are not talking about small rounding errors here. Trusting that simple ideal gas law could lead to calculations that are off by just a staggering amount.
500%. Can you imagine trying to manage a multi-billion-dollar energy asset when your most basic math could be that far off? That is an economic and a safety disaster just waiting to happen. So clearly, engineers needed a much, much better tool for the job.
And that brings us to the hero of our story, a really elegant engineering solution called the gas compressibility factor, or as pretty much everyone in the field knows it, the Z factor.
Just look at how brilliant this solution is. Engineers took the ideal gas law, and they just added one letter, Z. This Z factor is a correction term that basically bundles up all those intense real-world effects, the molecule size, the attractive forces, all of it, into a single powerful number. It's the bridge that connects the perfect model to the high-pressure reality deep underground.
So how do you find this magic Z value? Well, for decades, this chart, which was developed by Standing-Katz way back in the 1940s, has been the go-to tool. Engineers calculate two special values based on the reservoir's pressure and temperature. You can think of them like standardized coordinates, and they use those to pinpoint the exact Z factor on this graph. It's a truly brilliant practical solution to a really complex physics problem.
But of course, the real world loves to throw in another curveball. Natural gas is almost never pure. It's actually a cocktail of different gases, and some of them aren't even the valuable hydrocarbons we're after.
So a typical gas stream is mostly methane, sure, but it's also got other valuable stuff like propane and butane. But critically, it can also contain these non-hydrocarbons, things like carbon dioxide, corrosive hydrogen sulfide, which is what makes gas sour, and nitrogen. And every single one of these components slightly alters the behavior of the entire mixture.
Yeah, even just a tiny amount of an impurity, like CO2, can throw the calculations off. So, for maximum accuracy, engineers have to apply another correction. They adjust for these non-hydrocarbon gases before they even go to the Z-factor chart. It's this extra layer of precision that gets the model as close to reality as humanly possible.
All right, so let's pull all of this together and see how these concepts are actually applied in a practical, step-by-step process.
This right here is what an engineer actually starts with. a detailed composition analysis straight from the reservoir. It shows the exact percentage of methane, propane, and, just as important, those impurities like CO2 and nitrogen. This recipe is the unique fingerprint of the gas they're working with.
And here's the full workflow in action. First, they analyze that gas fingerprint. Second, they convert the reservoir's real pressure and temperature into those special, standardized values that work with the chart. Third, they use those values to find the all-important Z factor. And finally, with that magic correction number in hand, they can accurately calculate the real gas properties.
So why on earth do they go through all this trouble? Well, because getting this invisible science right is absolutely critical. It's for managing our energy resources efficiently, for knowing exactly how much gas is in a reserve, and for ensuring the safety of every single operation. Ultimately, it's this hidden, brilliant science that helps power our world.
Which kind of leaves us with a bigger question, doesn't it? This kind of invisible, super clever science is everywhere, not just in the energy sector. What other hidden complexities are quietly powering the technologies that all of us rely on every single day? Thanks for joining us on this deep dive.